Okay, so welcome back. Now that we have, excuse me, make sure I get this lined up. Okay, I do good. Okay, so now that we have gone through how to solve the Solow model analytically, let's take a look at what the Solow model looks like when it's graphed out, because the graphing might help this make a little bit more sense. So what I want to do when I graph this guy is I want output on the vertical, and I want capital on the horizontal. So what I'm doing is I'm graphing output y as a function of capital K. Now I'm going to graph output y equals a times k to the alpha. So this is my output function. So we can see it's increasing everywhere like I had said before, right? But it has a diminishing marginal product of capital, meaning it's going to be increasing everywhere, but as we keep adding more capital, the amount that the capital will be contributing to output is going to fall. So if you remember the Inada conditions, right, the limit as k goes to infinity of the marginal product of capital goes to 0. What does that mean? Well, as k gets larger and larger and larger, the slope of the production function with respect to capital approaches 0. So the more capital we get, the more capital we add in, the less it contributes to output. And if the rental rate of capital is equal to the marginal product of capital, so the price of capital is equal to basically how much capital can contribute, we have a lot of capital already. What is the price of capital going to be if we've got a lot of it? Well, it's going to be relatively low. As capital approaches infinity, the marginal product of capital, the rental rate of capital, will approach 0. So that explains the slope of this production function. But we have investment. So let's graph out investment. Now, if you remember, like I've said a couple of times already, investment is savings, and it's a constant fraction of output. And before I draw investment, I just realized how crooked this horizontal axis is, and it's driving me nuts. So let's go ahead and fix that. Let's see how it looks from your perspective. Okay, it looks a little bit better. So let's draw out investment. Now, investment is equal to savings, and savings is a constant fraction of output. Thus, investment is a constant fraction of output, which means it's this guy just scaled down. Go ahead and change that because slope never goes negative. Ah, son of a bitch. I know your teacher just said a bad word. Big deal. Probably read parts of my textbook already. It's probably not that much of a surprise. So, investment, son of a bitch again. So investment is going to be the same function of this, just scaled down. So whether we're here at this point, right, this will be the same fraction of output that it is over here. Output is greater, so that fraction, the fraction will be the same, but the amount being saved, the amount being invested, is going to be larger. But as far as the amount of output, or the share of output that composes investment, is going to be the same here as it is here, here, all the way out here, over here. You get the point. So this is the investment curve. But we've got one other curve that we want to look at. And that is depreciation. It's supposed to be a straight line. So depreciation is a straight line. And the slope of the depreciation line is delta. So whatever the rate of depreciation is going to be describing what the slope of the depreciation line is. Now the steady state occurs So the steady state occurs right here, where depreciation crosses the investment curve. And there's a steady state that's achieved here. However, I'm going to draw this dotted line up. So the steady state capital is reached when the depreciation line equals investment. But if I just draw this line up and then over, this is going to be steady state output. So once I find steady state capital where depreciation is equal to the investment curve, that's the input of capital in the steady state. So when I took steady state capital, S times A divided by delta to the power of 1 over 1 minus alpha, and I wanted to find what steady state output was, I took S times A over delta to the power of 1 over 1 minus alpha and plugged that in for K in the output function. And that gave me steady state output. What I'm doing here is I've got my steady state capital and it's plugged into the output curve, and that generates steady state output. Now let's look at the investment curve, right? Steady state capital is achieved when delta K is equal to I. So what steady state do we think this is? I'll give you a couple of seconds to think about it. If I had the Jeopardy theme song, that would be incredible, but I don't. Okay. This is steady state investment. Why is that steady state investment? Well, if you remember, investment is equal to savings is a constant fraction S of output. So when steady state capital crosses or is met when the depreciation line crosses the investment curve, that's going to generate steady state investment. So this distance, the distance from the origin up to ISS, tells me how much is being invested. We'll denote this IT. Like that. So if this total amount is what's being produced, and I know what's being invested, so if I know what's being produced, I know what's being invested, thanks to Walras' law, I can infer that this stuff is what's being consumed. And this is what the Solow model looks like in the steady state when we graph it out rather than just math it out. So let's do a little exampling here to see what's going to happen if certain parts of this will change. So I'm going to draw the graph again. I'm going to output. Investment. And I'll have depreciation. Like this. So this is our initial steady state. Steady state capital generates steady state investment and steady state output. But now, let's suppose that depreciation increases. So depreciation is going to increase. What's going to happen? Well, let's think about this. So if depreciation increases, depreciation goes up. Well, let's think of it this way. All right, so I've got steady state capital. Now in steady state capital, if depreciation goes up, it's in the denominator. So if depreciation goes up, this guy goes up, then what's going to happen is steady state capital is going to go down. Right? Is anything in the denominator gets larger, right? His overall fraction gets smaller, meaning KSS is going to get smaller. So we need to go, all right, what's going to happen here? Depreciation goes up. Well, when depreciation increases, the depreciation line, delta K, gets steeper. It gets steeper because if the slope of this is delta and delta goes up, well, the slope's going to increase. It gets steeper. Call it delta 1 KT. Now originally, steady state capital existed here, but with the new depreciation line, steady state capital is now over here. Call it KSS prime. So when steady state capital falls as a result of depreciation, steady state investment also falls. And then we just draw this straight up and over. Steady state output falls. So if investment and output fall, we can assume consumption will fall as well. Why is this happening? Well, in the steady state, right, we're investing just enough capital to keep everything steady. Keep everything going along a flat line. If depreciation increases, the capital is going to fall. Why? Well, because the amount of capital we're dumping in now is, instead of being added to the capital stock, more capital is being required to replace the existing capital that's fallen apart. So as more capital begins to fall apart, if you're dumping in 10 units of capital every single period, where initially 1 unit of capital was falling apart, you're adding 9 units of capital all the time. But now what's happening is, let's say the depreciation rate increased from 0.1 to 0.5. Well, now you're only dumping in 5 units of capital. Right? You're still dumping in 10 units of capital total, but only 5 of those units of capital can actually be used for new capital, to add to the new capital stock. So because the amount of capital being added in is the same, but the amount of capital being replaced is increasing, we're not adding as much anymore. So steady state investment is going to fall. And if investment falls, then the available capital stock for production falls, output falls. And if output's going to fall, well, consumption will fall as well. So that's what happens if there's an increase in the rate of depreciation. Now let's look at what happens if there's an increase to the savings rate. Draw our graph again. Isn't this a blast? Drawing graphs. I'm just going to write IT. Actually, you know what? Investment equals savings, which is a constant fraction of output. So we draw out Solow model in the steady state again, like this. All right, but now, instead of the depreciation rate increasing, the savings rate's going to increase. If the savings rate goes up, investment is going to shift up. We'll call it IT prime. ST prime equals S prime times YT. Right, so this whole curve just pivots up, pivots out. Right, now what we want to do is go, okay, where does this intersect with depreciation? Well, it intersects over here. It intersects at a higher level of the capital stock, because if we're saving more, we're consuming less. So by saving more, we get to add more to the existing capital stock. And we get to produce a little bit more. Like that. So if the savings rate increases, steady state capital increases because we're adding more to the capital stock, so the capital in the steady state will be higher. Steady state investment will increase. Steady state output will increase. But this comes at a cost. And the cost that we face here is steady state consumption will fall. If we want to save more, we have to consume less. If we consume less, consumption falls for investment to rise. But if we note, right, the two examples we just saw by changing S and delta, right, if we think, rewrite steady state capital again, like this, right, if delta went up, steady state capital fell. But here, savings goes up, steady state capital goes up, because savings is in the numerator. So the good stuff here is in the numerator of this solution. The bad stuff's in the denominator. The bad stuff's in the denominator because if the bad stuff goes up, it's going to drag down steady state capital. The good stuff's in the numerator because if the good stuff goes up, it drags up steady state capital. But for both a change in the savings rate and a change in the depreciation rate, we stay on the same output curve right here. There is no new output curve that we're looking at. So what happens if there's a new output curve? I'm glad you asked, Jeremy. Oh, thanks. Thanks, strange disembodied voice. That's totally not just within my head. Oh, you're welcome, Jeremy. COVID's been tough. Let's look at a change to A. Now here, I've got output, I have investment, and I'm just going to do depreciation as another blue line. Okay, so here, we got steady state capital occurring here, it generates steady state output, YSS, and shift over here for steady state investment. Right, but there's a change in A. Now if I write out steady state capital again, right, if A changes, it's in the numerator, it's a good thing. Steady state capital will be expected to increase. Let's draw out what actually happens if there's a change in A. Use the purple marker again. When A changes, it shifts Y. Why is it shifting Y? It's shifting Y because it's a function, Y is a function of A. A goes up, Y goes up. Right? But Y here is graphed out as a function of K. It's not a function of A. So if we change K, we move to a new point on the existing output curve. But if we change A, this isn't A, this is K. So if we change A, well, the curve is going to shift. So let's say A increases. A goes up, that's going to pivot the existing production curve up. We'll call it YT prime equals AT prime times KT to the alpha. Right, but is that all that's going to happen here? No. Since YT shifted, an investment is a constant fraction of output, then investment will also shift up. We'll denote it IT prime. I need to extend this depreciation line a little bit. Like that. Say IT prime is equal to S times YT prime. Now the savings rate didn't change. Right? The rate at which we are saving didn't change, but because investment shifted up, we're still saving the same amount of output, the same fraction of output, but overall savings will increase. But if we're saving a quarter of our output for the blue and black lines, then for the pink and purple, it's still a quarter of output. It's just that quarter of output is a much larger number now. So here, we look for the intersection point between investment and depreciation. Call it KSS prime. And again, we will draw this dotted line up the new production curve. Call it YSS prime. And then here we have investment in the steady state, call it ISS prime. So investment increases, output increases, consumption will increase. Let's look at this. There's a shock to A. Steady state capital goes up, steady state investment goes up, steady state output goes up, steady state consumption goes up. So when we talk about the change to depreciation, well, that's just stuff starts falling apart more. When we talk about the change to savings, well, people just decided they wanted to save more. How are we going to interpret this change in A? Well, remember I had said before that A was a source of technology shocks. So if technology were to enter the model, it enters through A. Called total factor productivity. and it lets us produce more efficiently. So if there's a total factor productivity shock, what happens is there's an invention, there's an idea, there's something new that's created, something new that's generated within the economy. I'll stand over here so you can keep copying this stuff. There's something new that happens in the economy that wasn't done, that wasn't used before, that lets us use resources more efficiently. We get to produce, we get to generate output more efficiently. So we get to make more with less, so to speak. Now, a total factor productivity shock, like I said, could be an invention, could be a cool new idea, a new way to produce things. What would be an example of that? Well, the development of the computer is definitely an important one, right? When the computer gets developed, goes through some issues of, development, kind of needs to be worked out a little bit before people can really find a widespread use for them. But as it becomes more and more developed, people get more efficient uses out of computers. So we can start using computers to help us figure out how to build rockets, figure out telemetry of rockets. We can use computers to take this class. We can use computers to make guitar amps not have to have tubes anymore. We can just use basically a computer processor and plug a guitar into it, and boom, it sounds like any guitar amplifier you want. We can use computers to do our homework. We can use computers to write books rather than having to use our hands. So as it finds more and more of a widespread use, we can even use computers to go to, at a restaurant, we can use a computer to order from a menu, so we don't even have to talk to the server when we're ordering our food. Right? Computers have found uses everywhere. That would be a positive technology shock. Another technology shock would be, let's say, for those of you that like Star Trek, the replicator gets invented. Right? The replicator basically goes like, well, energy and matter are interchangeable, so you can tell a computer to go, all right, well, I want you to reorganize, take some energy, reorganize it into matter that's consistent with a certain type of food that I want. Right? Well, if we're using antimatter to power that, well, it's probably a pretty efficient way of generating this stuff, probably really cheap to do it. So once we figure out how to reorganize energy into matter to make it food, well, we get food more easily. That's probably going to be a positive technology shock. On the other hand, if there's a negative technology shock, let's say, Haiti gets hit by an earthquake, it's really, really bad, wipes out a good chunk of the country. Well, all of the arrows that you see here would just be flipped. Right, so let's say this is the original level of output, this is the original level of investment. There's a negative technology shock, it's going to shift everything down. So when there's a negative technology shock, AT drops, steady state capital drops, steady state investment drops, steady state output would drop, steady state capital would drop. Now the reason A is included here is because the original production function was a function of capital and labor. So we're taking these measurable inputs of capital and labor and putting them into a regression model that we can model statistically, and we go, okay, if output's a function of capital and labor, then anything that is not capital or labor but still driving output has to be technology. It has to be a technology shock. So anything that's not capital or labor but changes output one way or the other is technology. And that's what this AT term is. Now, as I had said before, if there is no technological change, A is simply equal to 1. If we have positive growth, A is larger than 1. There's negative growth. A is less than 1. But if you remember some of the initial conditions we talked about with the model, namely the shape of the production function and some of the assumptions we had, A is always positive, and it's non-zero. A can never be equal to 0 because we have to have positive output, and it can never be negative because, again, we have to have positive output. So if there's negative growth, A is less than 1, but it is always going to be greater than 0. If there's positive growth, A will be larger than 1, in case we don't have to worry about that 0 part, because if it's larger than 1, it's going to be larger than 0. The amount that it will shift up or down is dependent upon the amount of worth that this new technological change, this new invention provides to the economy for it shifting up. For shifting down, if it's going to shift down, well, it's, again, the magnitude of the drop is dependent upon how much of a disaster that country faces. And that will wrap up the graphical explanation of the Solow Growth Model. Thank you. Peace. I have no idea why I'm doing that or how much longer that's going to keep happening, but if it keeps happening, I guess it's just going to keep happening.